Hello everyone, welcome to Vihari Academy. This is Dr. Rekha Piliadula, researcher by profession. In my previous video, I have discussed about vector calculus, the basic concepts, and in this video, I am going to continue the remaining concepts of vector calculus. With no further delay, let us start the discussion. So now let us see what is vector calculus. In order to understand vector calculus, we need to have the knowledge about different kinds of operations or the operators that we can operate in between two vectors, and the corresponding algebraic operations. So now let us see what are the different kinds of operators that we have in order to operate between vectors. The major operators include addition, and multiplication. Now let us see what is addition. If we have two vectors, a bar and b bar, then addition can be symbolically represented with a symbol plus here. Now if we have a vector a bar, which is represented as xi cap plus yj cap plus zk cap, and the other vector b bar, if it is having its components as specified as x prime I cap plus y prime c cap plus z prime k cap, then how we can perform the addition between these two vectors is a bar plus b bar is equal to the summation of likely compounds. That means we have to add the components along a single direction. That means we should add the likely compounds, that means along I cap direction, and the compounds along j cap direction, and the compounds along k cap direction together. That means here we can get x plus x prime plus y prime plus z prime, and now x and x prime are along I cap direction, y and y prime are along j cap direction, z and z prime are along k cap direction. This is how we do addition between two vectors. And now let us see how we can represent this addition geometrically. Say for example, we have a bar. We can represent this a bar like this geometrically, and if there is another vector b bar, then how we can sum up these two vectors? We can add two vectors when the ending of one vector will be the starting point of another vector. Geometrically, when we have this kind of representation, we can add both the vectors in such a way that the resultant vector will start from starting point of the first vector and ends at the ending point of the second vector. That means this will be a bar plus b bar. If we have to subtract b bar from a bar, that means how we can represent a bar minus b bar. This can be written as a bar plus of minus b bar. That means it also can be represented as addition between the vector a bar and the opposite vector of b bar. what is the opposite vector of b bar, which is represented by minus b bar, is another vector, or the vector which is having the same magnitude as b bar but is in opposite direction of b bar. That means the minus b bar can be represented as like this. Now let us see what are the laws that can be obeyed by addition of two vectors. The first law is commutative law, which means that adding b bar to a bar and b bar to a bar will give the same resultant vector. And what is the second law? That is associative law, which means that when there are three vectors a bar, b bar and c bar, adding the resultant of b bar plus c bar to a bar, or adding c bar to the resultant vector of a bar and b bar will be the same. And the third law is distributive law. That means any scalar which multiplies the resultant vector of addition of a bar and b bar will be the same as the addition of the vectors resulted by individually multiplying the scalar with a bar and b bar. Now let us see multiplication. The multiplication between two vectors can be done in two different ways. The one is scalar multiplication, or we can say scalar product, and the other one is vector product. So here the scalar product is defined with an operator. Symbolically we can represent it with dot, so that it is also called as dot product. So if we have two vectors a bar and b bar, we can represent the scalar product between these two vectors as a bar dot b bar, which will give a scalar as the product resultant of this multiplication. The resultant quantity is a scalar, which can be represented as ab cos theta. So geometrically, when we define a bar and b bar originated from a point and having an angle theta between them, then if we do the multiplication through a dot product, when we do dot multiplication between these two vectors, it can be as a times the projection of b vector along a bar, or otherwise we can term it as b times the projection of a vector along b bar direction. That means here, if we consider b bar, we can split this b bar vector into two components, horizontal and vertical components. The horizontal component will always be in the direction of another vector that we are going to multiply with, and the vertical component will be perpendicular to this horizontal component. That means the angle between these two components will be 90 degrees. So now, as per its definition, if we consider a, and the projection of b along a bar direction will be b cos theta. This can be considered as horizontal component of b bar vector, or otherwise projection of b bar along a. And here a and b can be defined as the magnitudes of these vectors respectively. Now let us see how we can represent this in component forms along Cartesian coordinate system. If we have two vectors a bar and b bar, then how we can do a bar dot b bar? If a bar is defined as xi cap plus yz cap plus zk cap, and b bar as x prime I cap plus y prime j cap plus z prime k cap. So now this is the component representation of A bar and B bar. That means the magnitude of A bar along x-axis is x, and the magnitude of A bar along y-axis is y. The magnitude of A bar along z-axis is z, with their unit vectors along x as I cap, along y as a cap, and along z as k cap. The same can be defined with B bar as well. So now we have the components of A bar along 3 different axes and component of B bar along 3 different axes. How we can do dot product between these two vectors with respect to their components. As x, y, z, x prime, y prime, and z prime are the magnitudes of the vectors along 3 Cartesian coordinate axes, the multiplication between them will be as normal multiplication between any two variables or any two numbers. But here the most important thing is we are dealing with vectors, so that we are dealing with their directions as well. So now it is very important to define the dot product between the unit vectors of the two vectors. For this purpose, we have few rules which we can derive with the basic definition of dot product. Here I, j, and k are the unit vectors along x, y, and z directions, having their magnitude as 1. So now let us see how we can multiply the unit vectors. We have 3 directional unit vectors, that means unit vectors along 3 coordinate axes, so that we will have the combinations of dot product between them in such a way that I cap dot I cap, j cap dot j cap, k cap dot k cap is 1, because if we have the basic definition of two vectors with the dot product, that means A bar dot B bar is equal to AB cos theta. That means I cap dot I cap is equal to modulus of I cap and the modulus of I cap cos theta. Here we know that magnitude of I cap is 1 and the magnitude of I cap is 1, so that we have 1 into 1 1, and cos theta is 90 degrees. Sorry, theta is 0 degrees, because this is dot product between I cap and I cap, which are along the same direction. That means both these unit vectors are parallel vectors. So cos 0 is 1. So 1 into 1 is 1. That's how we arrive at I cap dot I cap as 1. And the same thing will be for j cap dot j cap and k cap dot k cap. And now another set of combination we can have between the unit vectors is product between x unit vector with y unit vector, and its reverse operation will be 0, because the angle between I and j is 90 degrees, cos 90 is 0, so everything will become 0. And the other combination we can form is j cap dot k cap, which will be equal to k cap dot j cap, and is again 0. And another combination is k cap dot I cap, which is equal to I cap dot k cap. Again the result is 0. With this thing in view, we can only have the combination between I dot I, j dot j, and k dot k, because all other combinations will become 0. So now let's write A bar dot B bar. X prime plus y prime plus z prime. Now let us see how many laws it will obey. So now let us see commutative law. That means A bar dot B bar is equal to B bar dot A bar. So the dot product between two vectors is commutative. And coming to the associative law, it does not obey associative law. What does it mean by associative law? A bar dot B bar dot C bar. And we should be able to prove that A bar dot B bar dot C bar is equal to A bar dot B bar dot C bar. But here, as B bar dot C bar itself will lead to a scalar, and here we have another vector, and the dot product is not possible between a vector and a scalar. So in the case of dot product, associative law is not obeyed. Coming to the distributive law, how we can define it? A bar dot b bar plus c bar, this is equal to a bar dot b bar plus a bar dot c bar. So dot product is commutative and distributive but not associative. Now let us talk about vector product. Vector product is usually defined with an operator cross, which is why it is called cross product as well. And if you have two vectors, a bar and b bar, the cross product between these two vectors is defined as a cross, and the resultant of this vector product or cross product between a bar and b bar will lead to another vector. That is why it is called vector product. How we can define vector product? A bar plus b bar is defined as ab sine theta n cap. Here n cap is direction of the resultant vector of a cross b, that means a bar cross b bar. The direction of n cap will always be along the perpendicular plane of the plane that is consisting of a bar and b bar. That means if we have a bar and b bar with an angle theta between them in xy plane, the resultant of a bar cross b bar will be along z plane, along z axis. That means like this. Now how we can define this a bar cross b bar when a bar and b bar are defined in their component form? Say for example, we have a bar as xi cap plus yj cap plus zk cap, and b bar defined as x prime I cap plus y prime j cap plus z prime k cap in their component form. Then how can we write a bar cross b bar? To find it out, we have to take the modulus, taking into consideration as a bar and b bar defined in terms of 3 by 3 matrix, so that a bar cross b bar will become the modulus of I cap j cap k cap x y z, and here the components of b bar that are x prime, y prime and z prime. This is how we can define a bar cross b bar in component form. Now let's see what are the laws that are obeyed by vector product between two vectors. Vector product between two vectors is not commutative. That means a bar cross b bar and b bar cross a bar are not equal. In fact, they are anti-commutative. Then let us check associative law. A cross b cross c is not equal to a cross b cross c. And coming to the distributive law, cross product is distributive across vectorial addition. That means a cross b cross plus c is equal to a bar cross b bar plus a bar cross c bar. So vector product is non-commutative, non-associative, but only distributive. Now we have seen addition, scalar product and vector product. Let us summarize the laws that are being obeyed by different operations of these operators. Say for example, now let us write addition dot product and cross product. Let us check whether they obey commutative law, associative law, or associative and distributive. Addition of two vectors is commutative, associative, and distributive. Coming to the scalar product, a bar dot b bar, that means dot product, it is commutative but not associative and is distributive. Coming to this cross product, it is commutative it is not commutative, not associative, but only distributive. So if you remember this tabular column, you can answer any question that can be asked from this concept. And now, along with this, another summarizing thing that we have to do here is the rules of scalar product and vector product. For scalar product, I dot I, j dot j, or k dot k equal to 1, and all other combinations will be 0. And for the vector product, I cross j is equal to k, because the resultant of cross product between any two vectors will be pointed out perpendicular to the plane that is consisting of I cap and j cap. So I cross j will be along k cap direction. J cap cross k cap is equal to I cap. K cap cross I cap is equal to j cap. And if we reverse the order, then j cap cross I cap will be minus k cap. K cap cross j cap is minus I cap. I cap cross k cap is equal to minus j cap. Here I dot I, j dot j, k dot k is 1, and remaining everything will be 0. For vectoral product, that means cross product, I cross j equal to k, j cross k equal to I, k cross I equal to j, and the reverse order will change the direction. That means j cross I is equal to minus k cross j is equal to minus I cross k is equal to minus j cap. I can tell you the order to remember this very easily. I mean the vector product rules. Just to take I, j, and k. Always follow from I to j, then j to k, and k to I. That means I cross j, j cross k, k cross I. This is the forward motion of the order. And if in case the order is reversed of this direction, then the resultant will be in opposite direction. This is how we can remember. The next concept is triple product. We have scalar triple product and vector triple product. Now let us see the scalar triple product. Because the cross product between any two vectors gives the resultant of another vector, as we know, the cross product between any two vectors, let us say vector 1 cross product with the second vector, this will result on another vector, so that the cross product between two vectors can be either dot producted or cross producted with another vector. So based on this concept, we have two triple products, scalar triple product or vector triple product. Now let us discuss about scalar triple product. Scalar triple product is a product between three vectors having cross product between two vectors which is dot producted with another vector. So this is called scalar triple product. How we can define it in terms of its componental form? Let us see. If we have two vectors a bar and b bar defined in such a way, and c bar as x double prime I cap plus y double prime c cap plus z double prime k cap, then how we can define the scalar triple product, which is defined by a bar dot b bar cross c bar. This can be defined as a modulus between the magnitudes of three vector components. That is, the first vector component, a bar vector components are x, y and z. Let us write them x, y and z. And now second vector components x prime, y prime and z prime. Let us write them. And third vectoral components x double prime, y double prime and z double prime. As this a bar dot b bar cross c bar, which is scalar triple product, it leads to the scalar quantity. That is why we do not have any directional specification in this. Now let us see the other regulations or rules that are followed by scalar triple product, which we have to define here. The first rule we have to define, or we have to remember in scalar triple product, is a dot b cross c is equal to b bar dot c bar cross a bar, again which is equal to c bar dot a bar cross b bar. And a bar dot b bar cross c bar is equal to minus of a bar dot c bar cross b bar. This is because we are just interchanging the vectors that are being operated with cross product. That means we know the cross product is anti-commutative when it is operated between two vectors. So when we interchange the vectors, that means b bar cross c bar is equal to minus c bar cross b bar. That is why we have this negative sign here. And the third regulation we have to remember is we can interchange dot product and cross product. That means we can interchange dot product and cross product. That means a bar dot B bar cross C bar is equal to A bar cross B bar dot C bar. Now let us discuss about vector triple product. Vector triple product is defined as A bar cross B bar cross C bar. This vector triple product can be calculated by using BAC minus CAB rule, that is A bar cross B bar cross C bar can be defined as BAC minus CAB. Put the brackets for the last two vectors having dot product between them. Let me write it again. BAC minus CAB rule. That means I can give you a sentence to remember this formula. If you have to go back to home, you need a cab, but for that you have to pay some money so that your balance will be minus. So this is the basic sentence that you can remember to reproduce this one whenever needed. And for this, just remember that always put bracket for the last two vectors with dot product within the bracket. This is how you can simplify this vector triple product. And in this vector triple product, always remember that it will lead to a vector. There is another important rule that we have to remember is law of cosines. What does it mean by? If a vector C bar is defined as A bar minus B bar, then we can write it as C square is equal to A square plus B square minus 2AB cos theta. This is called law of cosines. Now let me summarize whatever I discussed in this video. The first one we have discussed is different types of operators, that is addition operator and multiplication operators. In multiplication operators, scalar product and vector product are the two types. Then we have checked the laws, mathematical laws that are obeyed by these operations. That means addition, that is A bar plus B bar, obeys commutative law, associative law and distributive law. The dot product is commutative but not associative, but it is distributive. And the cross product is not commutative, not associative, but it is distributive over addition of two vectors. And the next thing we discussed is the multiplication rules through dot product between two vectors. That means I dot I, j dot j, k dot k is equal to 1. The unit dot product between unidirectional unit vectors leads to 1. All other combinations leads to 0. But in the case of vector product, the cross product between I and j is equal to k cap. J and k is equal to I cap, k and I is equal to j cap. When we reverse the vectors, the resultant will be with a negative sign. And coming to the scalar triple product, these are the rules we have to remember. That is A bar dot B bar cross C bar is equal to B bar dot C bar cross A bar is equal to C bar dot A bar cross B bar. Having that, the order is persisted from A to B to C. That means here order is A, B, C. When it starts from B, the order is C and then A, B, C, A, and here C, A, and B. A bar dot B bar cross C bar, when the vectors with cross operation are inversed, the sign will be negative. Sign of the resultant vector will be negative. And A bar dot B bar cross C bar is equal to A bar cross B bar dot C bar. That means we can reverse or we can replace the dot product with cross product and cross product with dot product. Even then the resultant will be the same. Then in vector triple product, we have to remember this BAC minus CAB rule, and always the resultant of vector triple product is a vector, but the resultant of scalar triple product will always be a scalar. That's all we have to remember. Let's meet with another video with more information. Thank you.